Hello, I'm Pooja Oza, and I'm a PhD student working with Dr. Laura Dietz, who is also co-author of this paper at University of New Hampshire. I'm here to talk about our paper titled Which Entities Are Relevant to the Story. Nowadays, information is spread across various sources or articles. Especially the news stories are spread across different articles and span over various timelines. Sometimes users have the information need of synthesized stories of various topics, such as COVID-19 or radiocarbon dating or the 2020 US presidential elections. To construct and present a summarized story from different sources to the readers, it is important to understand and capture complex relations or connections that are present between different articles of the story. In our work, we focus on the first step of such summarized story construction, which is identification and retrieval of entities that are relevant to the story. This task resembles entity retrieval task, but it's different. In entity retrieval task, it is focused on retrieving the entities with precision. Whereas in our work, we focus on retrieving a list of entities that are relevant to various aspects of the story. So, for example, if we search for the query President of the United States on search engine, it returns the entity Joe Biden. This entity retrieval needs to be precise, while the story construction entity retrieval needs to cover various aspects of the story. So, for example, the query radiocarbon dating should give information about the scientists involved and the laboratories that were involved and the chemicals or the compounds that are needed for radiocarbon dating, etc. In our work, we define the task as given a query input, we retrieve a list of entities that are relevant to the query. Each entity in the retrieved list of entities is associated with a relevant scope. We assume a general purpose knowledge base and a large text corpus is given. We envision our system to take two different types of inputs. The first input is a short text, such as 2020 US presidential election nominations or radiocarbon dating background history, which we call as a story request. The second type of input consists of a list of multiple story requests that are connected to a larger theme. So, for example, a list of story requests, such as radiocarbon dating samples, radiocarbon dating background history, are connected to a larger theme of radiocarbon dating. We define this as multi-story query request. So how do we identify and retrieve entities that are relevant to a story? We do that through relations between the entities. A connection or a relation between two entities indicates relevancy. And especially for a summarized story construction, it is not just about finding out the connections between the entities, it is also about finding connections that are relevant to different aspects of the story. The previous work uses approach of keyword matching or using knowledge-based attributes such as entity categories or entity links to retrieve relevant entities. However, these approaches focuses on retrieving a small set of entities with high precision, whereas our work focuses on retrieving entities of varying degrees. We hypothesize that the text surrounding the entity mentions provide a strong indicator about the entity relevance. In contrast to the common approach of retrieving entities of keyword matching, which we refer to as KG entity here, We base our approach on pseudo-relevance feedback on the entity links in relevant text. We first retrieve text passages that are relevant to the query and then use occurrence of entities or co-occurrence of two entities in the retrieved text passages as indicator to retrieve relevant entities. We argue that the entities that co-occur in relevant text passages are likely to have a connection that is relevant, and thus these entities are also relevant. We make three different claims. In claim 1, we say that finding entities through relevant passages is more effective than finding entities through knowledge-based attributes. This is to demonstrate our claim that the common approach of keyword matching used in the entity retrieval is not as effective as retrieving entities through relevant text. In the second claim, we say that to predict the relevance of an entity, relevance retrieved through relevant passages is more effective than the knowledge-based links. In this claim, we demonstrate that the entity retrieval done through relevant text passages performs better than the entity retrieval done through the knowledge-based links such as inlinks and outlinks. We use different relevance factors of relevant text passages and knowledge-based links to study this claim. Our third claim is that the coupling patterns such as bibliographic count and co-coupling count can be improved by using relevance of the shared entities. In this claim, we study the impact of the relevance factor on the knowledge-based links. To demonstrate our claims, we study three different link types: relevant co-occurrence graph, unweighted link patterns, and relevance-weighted coupling. In our first link type, which is based on the relevance and the thought experiment that if we know which text passages are relevant to the query, then we can use the text-based signals to establish the links between the entities and also to determine the relevance of these established links and the entities. We start by retrieving text passages that are relevant to the query. And after entity linking these passages, we create entity pairs of the entities that are mentioned in the retrieved ranked text passages. So for example, one of the entity pairs that is formed in the given sample text passage is Martin came in and Samuel Rubin. We use three different indicators to rank the entities based on their relevance. The first indicator is co-occurrence relevance. If two entities that co-occur in the same passage, then we establish a link between the two entities and we weight the edge by accumulating the reciprocal rank of the passages in which the two entities co-occur. So in this indicator, we include the relevance factor by using the rank of the passages in which the entities co-occur. The second indicator is co-occurrence count. Similar to co-occurrence relevance, we establish the link between the entities if they co-occur in the retrieved passages. But we weight the edge between the two entities by the frequency of the co-occurrence. The third indicator is mention frequency. In this indicator, we count the occurrence of the entities in the retrieved passages. Our second link type is based on the knowledge-based links. Wikipedia is a large-scale knowledge base and represents the relations between different entities through inlinks and outlinks. Each Wikipedia article is an entity. We use 6 different types of indicators to identify whether a link exists between the two entities or not. And we determine the relevance score by taking the frequency. We consider outlinks, inlinks, bidirectional links, and undirected links. For these 4 indicators, We weight the edge between the two entities by taking the count. The rest of the two indicators are based on the coupling patterns. In bibliographic coupling pattern, we consider the outlinks that are shared between the two entities. In co-coupling pattern, we consider the inlinks that are shared between the two entities. Our third link type is a hybrid of the knowledge-based coupling methods and relevance-based approach. As we stated previously, the traditional coupling patterns such as bibliographic coupling and co-coupling do not consider any kind of relevance factor at all. So we introduce the relevance factor in the coupling pattern through the scores of the ranked knowledge base entries. Using this link type, we try to understand what is the impact of the relevance on the co-coupling, on the coupling patterns of the knowledge base links. We have two different indicators in this link type. Bibliographic relevance. The shared outlinks between the two entities are weighted by the relevance score of the ranked knowledge base entries. In co-coupling relevance, the shared inlinks between the two entities are weighted by the relevance score of the ranked knowledge base entries. So now once we get the scores of the entity pairs, how do we convert them to the score of the individual entities? We do that by accumulating the scores of all the entity pairs in which the entity is present. We do this for each indicator, so it gives us the scores of every entity for each indicator. Once we get the entity scores, we rank the entities indicator-wise as well as in combination. To combine these different indicators, we use the learning to rank framework, where we combine the top 4 best performing indicators of all the approaches. We use Track Complex Answer Retrieval Year 1 benchmark dataset to evaluate the ranking of the entities. The knowledge base is derived from the Wikipedia dump that preserves the entity links of the Wikipedia articles, and the text corpus is derived from the Wikipedia passages. We use 3 different types of evaluation metrics, mean average precision, R precision, and F1. As stated previously, we provide 2 different types of queries as an input. The first type of query is a story request, which consists of short texts, such as radiocarbon dating samples. In TRECCA Year 1 dataset, there are 1952 such story requests that are given as an input. Now let's see the results. Our first claim was that the common approach of keyword matching for entity retrieval is not as effective as retrieving entities through the relevant text passages. Looking at the results, the indicators of the relevant co-occurrence link type, which consist of co-occurrence relevance, co-occurrence count, and mention frequency, perform far better than the KG entity, which is based on the common approach of keyword matching. Our second claim says that retrieving the relevant text passages are more effective in entity retrieval than the knowledge base links. Looking at the results, the indicators co-occurrence relevance, co-occurrence count, and mention frequency of relevant co-occurrence type perform better than the knowledge base link indicators such as undirected, bibliocount, and co-coupling count. Our third claim was that the coupling patterns such as bibliographic count and co-coupling count can be improved by using relevance of the shared entities. For this claim, we got mixed results. As you can see, the co-coupling pattern improves when we include the relevance, but the bibliocoupling pattern does not improve when we include the relevance of the shared entities. The second type of input that we give is consist of a list of multiple story requests that are connected by a larger theme. In this second type of input, we combine the results of all the story requests that are given as an input and form the result of that particular theme. In TrekKaya, one data set, there are 132 such multi-story query requests. Similar to the story request, we see the same pattern in the multi-story request, in the multi-story query request. We observe that for both claim 1 and claim 2, the relevant text messages indicators perform far better than both common approach keyword matching and the knowledge base links indicators. For our claim 3, which says that the coupling patterns, bibliographic count, and co-coupling count can be improved by using relevance of the shared entities, we observe the same result as we did in the story request, which is co-coupling pattern improves with relevance, but the bibliocoupling pattern does not improve with the relevance. We suspect that the reason behind this is the small number of inlinks. To conclude, we observe that the relevant text of the entities is a strong indicator than the knowledge base links. It improves the result almost between 80% to 30%. Thus, we can say that the relevant text-based signals are more effective than the general purpose knowledge-based signals in retrieving relevant entities of varying degrees. We would like to thank NSF for supporting our work through NSF Career Grant. Thank you.